We're going to be focusing on musical instrument type things. So here is your simplest musical instrument. I don't know about you guys, but when I was a kid, we had this stuff we called joint grass. We were talking about it at worship the other day at home. My wife was, that's not a good name, joint grass. There are other names for it, but it's basically a thing that grows like bamboo. And so you have things like this, and you can pull them apart, and you have these little things you blow over the top of them, and it whistles. Just like that young lady with her Coke bottle, which of course is also probably not appropriate to talk about because Coca-Cola was originally cocaine cola, right? Bad. These days, of course, there's not cocaine in it. You blow over that and it makes a musical sound. Now, for making a musical sound, you need a couple things. One thing you need is a source for the sound. So when she's blowing over that bottle top, what's the source? It's her breath. Okay, then you need a medium for the sound to go through, which is just going to be air. And finally, you need somebody to receive it. Now, there is that, I consider, inane question. If a tree falls in a forest and there's no one there to hear it, doesn't make a sound. I consider it inane because I'm a physicist. And to a physicist, the sound wave is going to exist because we have A causes B, right? The purpose of that question is to question what is reality. Is reality what we perceive, or is it something outside of our perceptions? That's what that question is supposed to be about. We physicists aren't good with that kind of philosophy. So then you have to have somebody to hear it, though, if it's going to be appreciated. So in this case, she's blowing on it. How is that going to make sound? Okay, it produces vibrations. The worship book we go through in the morning is written by a biology professor, and he actually had something on. We're going through December right now, so if you were to read the same book, you probably wouldn't be reading it last week. But talking about this, and as a biologist, he was like, well, I don't really understand how it works, but something like this. Well, we're in physics, so we're supposed to understand how this works. When you blow over the top, you have air going like this. What does that do to pressure when the air is blowing over the top? It lowers it. So if you have a lower pressure above the tube than you have inside the tube, what's going to happen to the air inside the tube? Okay? You have a lower pressure above, a higher pressure below, it's going to push it out. So you're going to have air that comes up out of the tube. But when that air comes out of the tube, it disrupts the flow of the air over the top, and the pressure goes up above. And so then it goes back down. And so the sound wave is created initially by having an alternating force, because that air blowing up over the top, when it blows over the top, it pulls air up, but that air that was pulled up increases the pressure up there, and so then it goes back down, and that's how you get the whistle action for this. The next part is the tube is going to act like a resonator. Now, we talked about waves on a string. To make a nice sound on a wave on a string, what did we have to set up in terms of waves? Okay, something what? Okay, we had something to hold either end. So in terms of waves, we had for the wave on a string a standing wave that had a node at each end. And it could have been a half wavelength for the standing wave, or it could have been an entire wavelength for the standing wave, and so on. And so we found there that the length of the string had to be equal to, well, the wavelength over 2 times n is what I was trying to write, and I got myself confused. And so we were able to solve that to say that the wavelength that resonate had to be 2L over n. That's what we found for a string. Now, she's using a Coke bottle. I'm going to start by looking at a pipe that is open on both ends. So here's a pipe. And we're going to set up a standing wave in this pipe. Now, sound waves, what kind of waves are sound waves? They're longitudinal waves. They're waves where you have the displacement in the same direction as the wave travels. So displacement is going to be that direction as the wave travels through the tube. And we have regions of high pressure, regions of low pressure, the compressions and the rarefactions. Well, if the pipe is tube, going back to English, if the pipe is open at both ends, then where it's open, what is the pressure going to be at the open end? What's the pressure on your hand? You open to atmosphere and you have air pressure, the atmospheric pressure. So the pressure at the end is equal to the atmospheric pressure on both sides. And immediately, is Dalton, is that what you said it was? Your name? Todd? John. I really am going to have my hearing checked soon. I was so far off. Even when he corrected me, I was so far off. Okay, you're going to immediately say, I can't read his handwriting. I'm sorry. It's not the best handwriting in the world. That's what they told me in grade school when I got F's in it. So we have this pipe, and it has a fixed pressure at both ends. If I'm going to set up a standing wave, what do we consider a point where the value doesn't change? It's a node. So this is also going to have pressure nodes on either end. Well, if it's a node on either end, and we had a node on either end for the string, it's going to have exactly the same equation for the wavelengths. That is, the wavelength n is going to be 2L over n, where n was any integer, any counting number, 1, 2, 3, 4, 5. So we're going to have the same equation for the frequencies. Frequency was V over wavelength. So if I put in my wavelengths, I'll have the frequency sub n is equal to V. Now this is a sound wave, so I'm going to put V of sound just so we're clear, divided by my 2L over n. So the exact same equation that we had for a wave on a string is the equation that tells us what's going to resonate for a tube if it's open on both ends. And just like before, we call this frequency in parentheses the fundamental frequency. And we can have it play harmonics. Harmonics, any n. So n equals 1 is the first harmonic. N equals 2 is the second harmonic, and so on. Now there's another term. I was just talking to Denford before class as we were going over his demonstrations for the day. We also have the term overtones. Overtones, any n greater than 1, and the number for the overtones is equal to n minus 1. That is, if n equals 2, it's the first overtone, because it's the first one above n equals 1. If n equals 3, it's the second overtone, because it's the second one above n equals 1. Two different ways of talking about the different frequencies that will resonate. But they will resonate with different frequencies. And depending on how you play the instrument, you can make it shift the amounts of the different frequencies. In a few minutes, Denford's going to come up and illustrate that. But before he does, I have a couple more slides. Here is a closed tube. What's different about the previous one where it was open on both ends? We call it an open tube. What's different about this one? It's closed on how many sides? Only one. I know it's hard to tell because the other side's at the edge of the slide. Even if I'd moved it over because I have a black background, it'd still be hard to tell. But it's closed on this end and open on this end, and we consider that a closed tube. If it was closed on both ends, it would have no place for sound to come out. And then, well, we could consider it a hollow log that you beat on, but it's typically not a musical instrument. So we're still going to have four force. Frequency is the speed of sound divided by the wavelength. Speed of sound there, about 340 meters per second in air. The wavelength, if I look at this, now first thing you note is I set a pressure node at the open end. What part of a standing wave is it showing at the open end of this tube? What do you call it where you have maximum motion, as Rachel put in her potential test question from Wednesday? I know, I put her on the spot. It's the question you asked. Yeah, I didn't hear if you had an answer. Antinode. It's an antinode. So we have an antinode here. I'm going to put AN for antinode. And we have a node here. Well, that clearly is not pressure, because pressure should have had a node at the open end. What this graph is showing is the motion of the molecules of air. The molecules of air at the open end, they're free to move in and out. And it turns out in that situation you have the maximal motion in the standing wave. On the side where you have the barrier, they can't penetrate the barrier, so their motion has to come to a stop at the barrier. And so that's why you have a node for displacement at the closed end, an antinode for displacement at the open end. If we had done pressure, it would have looked just the opposite. Pressure would have had a node at the open end and an antinode at the closed end, because once again, at the closed end, you can push on that end as hard as you want. The pressure can go up and down, it doesn't matter. And for setting up the standing wave, it turns out that's going to be an antinode. So now we're going from antinode to node. Well, the shortest distance from antinode to node is a quarter wavelength. The second shortest distance is 3/4 wavelengths, and so on. So we find that the length is equal to an integer of 1/4 wavelength, but that integer has to be odd. Right, so here the length is 1 times 1/4 wavelength. Here it's 3 times 1/4 wavelength. Oh, you can't see my arrows, sorry. Here it's 1 times 1/4 wavelength. Here it's 3 times 1/4 wavelength. Here it's 5 times 1/4 wavelength, and so on. So if I solve this equation for wavelength, change back to the pen. I'm going to have to multiply by 4, so I'm going to have 4L divided by N, and therefore my frequencies notice I still have a fundamental frequency, but instead of being V sound over 2L, it's V sound over 4L. So the fundamental frequency for a half pipe, for a closed pipe, is 1/2 of the fundamental frequency for an open pipe. As the closed pipe should have a lower frequency. How does pitch relate to frequency? This was another question somebody turned in last class period. The higher the frequency, the higher the pitch. So the closed tube, having a lower fundamental, is going to have a lower pitch. Okay, I believe now it's time for Denford. Nope. I have just my little introduction on notes. Forgot I had the notes first. I swear it's before the clickers. First question. Music, something I actually really enjoy, is really based a lot on physics. The notes are physically derived. We're going to see the name Pythagoras on the next slide, because he was the first person to come up with explanations for things that sounded good together, things that had a consonant sound. And we are going to use the computer equipment up here to view what a sound wave looks like as the variation in pressure and analyze the frequencies present. Denford's going to have some fun. So the actual sound something makes is based on the frequencies present. And so Denford and I are going to do some demonstrations, and I need to change this so you can actually see what Denford's going to be doing. Okay, so the first thing I'm going to have Denford do here is, come on, I'm going to have him start the monitor. Okay, I'm going to have him pluck the string at the center. So go ahead and pluck it. Okay. Oh, dang it. My voice screwed it up. Go ahead and do it again. Okay, I stopped it so my voice won't screw it up. So here we have the waveform that was created when he plucked at the center. Now, if you look at that waveform, it's not perfect, partially because of the rate at which I'm collecting data. See, I think if I go like this, it'll actually, well, no. It'll make it look better, but you can't see the waveform. If you look, you see it has sine wave type things, but they're not consistent. They do repeat over time. It's hard to tell here in the time frame I have that they're repeating. Here I'm going to, it's going to look even worse, but go ahead and do it again. Now do it. Okay, here you can see the repeating. You see, here's the first one, dives down, comes up, smaller, smaller, little funny thing, dives down. The next one comes down, dives down. So here it's gone through one cycle from the beginning to here. Goes through another cycle to here, another cycle to here, another cycle to there. So it's a complex waveform. Now if you look down below, or on the right picture, you can see the frequencies present. So, Denford, I know we were talking about this, so explain to them what's going on with the frequencies present.
With the frequencies, you have the fundamentals right here, and then you have the overtones, which we talked about, which determine, fundamental will tell you about the pitch, and the overtones give you the difference, like, for instance, if someone is speaking, it would give you the different voices which we have. So, for instance, we could speak in the same pitch, but then...
He would have to get much higher in pitch for that to work, though.
True.
I could go like this, and I'm almost down there.
So we could speak in the same pitch, but then we'd still have a different voice because of the overtones which we have in the frequency.
So if we look at this, our fundamental, that's the pitch that it was playing. You can see it's going to be a little less than 100, reasonably low pitch. First overtone here, second one, third one's weak. The fourth, or actually, yeah, first, second, third. These are overtones. So the fourth one is bigger, fifth one a little smaller, sixth one bigger. That pattern is what gives us its sound. Now I'm going to have him repeat, but I'm going to have him pluck at about 1/4. So where it says 0.25 or 0.75. About right here. So I'm going to have him pluck at a different location. Is it the same pitch?
Oh, you messed it up.
Do it again. Actually, I'm going to come back to like this so we can go again. Okay, I stopped it here. I was smart. We can look at this waveform. It doesn't look the same. If I spread this out now, the fundamental is the same place. They're much wider because of me changing the sampling rate. But the distribution of the frequencies changes a little, and that's what gives it a different pitch. Or not a different pitch, but a different tone. So you can change the tone just by where you're plucking, like we said last class period. Okay, our next one is going to be, Oh yes, the tuning, right. Go ahead. Wait. I am being silly. I'm adjusting the wrong way. Okay. Okay, this will be better. Go ahead and do it again. You should, while he's going to pluck it and then tighten it, and watch the frequencies as he's tightening. Okay, it doesn't work out the best here. It's supposed to show you the pitch changing. Well, let's try it with the whistle. The whistle, I can change the length. What should happen to the pitch as the length of the whistle gets longer? Nope, got both answers. Well, you know, we can test this, right? Ready? Almost got there before it clicked again. When it got longer, what happened to the pitch? It got lower. Why? Because, now is this an open tube or a closed tube? It's open on this end only. This end is closed. Open on one end, closed on the other, we call that a closed tube. So this is a closed tube. This is the opening here. That's where the sound comes out. That's why Denver was holding the meter up, or the sound sensor up there. That's where the sound's coming out. This has a built-in whistle to make my life easier. I blow, air goes through this little constriction, and then comes over an opening. Well, the air blowing lowers the pressure, and it causes air to come out, which makes my air fly up over, and then the air that came out makes pressure higher here, so then my air goes in, goes back and forth, and that's what makes the frequencies. Now, I was blowing kind of soft when I did that. I could have blown harder. So if I go, when I blew harder, I got a higher pitch. Why would that be? Okay, the air was going faster, and as the air was going faster, it was causing a faster response in here, and so the rate at which it surged changed proportional to my air blowing. But this only resonates at certain frequencies, so I didn't hear a continuous increase in pitch as I blew harder. When I blew hard enough to have a significant amount of the oscillation in a higher frequency that would resonate, then we heard it. All right. For our next one, we're going to play with the open and closed tube. Oh, yeah, go ahead and do that. Show them. Okay, this here is just to show you what a pure tone should look like. You can see there's some artifacting because my time range is too broad, but it's a nice smooth sine wave. That's a pure sound. So when we play this tuning fork, we're getting a pure tone. Whereas when we played the stringed instrument, we had a tone that had different frequencies mixed and gave us a different sound. Now we're going to have our instrument be Denford. Let's hear some vowel sounds.
E, O, U.
Okay, you got too fast, my friend, too fast. So go ah and just hold the ah.
E, O.
Go again. Okay, so when you look at that, it's hard to get the range right because as I change the range, the frequency bends change. When you look at that, an ah, a nice consistent ah, I have a higher voice that makes it easier. Denver with his lower voice makes it harder. So, ah, there's what ah looks like. What do you see there, Denford?
The overtones are much lower as you go further down, but the pitch is quite high.
No mocking here. Which is the strongest overtone?
The third.
I don't know why it just shifted, but it was actually the third overtone or fourth harmonic was the strongest one. See if I can. Dang it. Okay. So in this case, the third came out the highest. The fourth was higher than all the rest except for the third, right? Now I'm talking harmonics. And then the fifth was low and the sixth came up again. So that's what an ah sound looks like. Now let's go to E. E. Really? To make it good, I have to have a high sampling rate. But to see it, I have to change it. E. Okay, I'm at 20.6, in case anyone cares for the hertz. So for the E, there's really not much after the 400 hertz. And I'm pretty sure it's here is where my fundamental was. So it's really only the first two harmonics there for E. Ooh, A, O, A, E, ooh, A, O. As you look at those, you see what we call the formants, the different frequencies that make up a vocal sound so that we can differentiate them. I believe that's it for this. Oh no, we have the one more. This one here. So now what we're going to do is play this, look at the waveform while it's playing, and then I'm going to cover the bottom while playing it. Ow, hit my tooth. Not the one I broke on Monday. Okay, you see the shifts when I cover it and not. I'm going to just go away from that now. Different pitch because it has a different fundamental. Okay, Denver's going to go to his seat, and then he's going to come back later on for his coup de grace, and he'll show you how beats work. All right, I believe we are ready for our first clicker question. Not quite, but we are close. So we've looked at different formats, and now we're going to talk about tuning. Our clicker questions are going to be about tuning. So Pythagoras, 500 BC, roughly 500 years before Christ. That's what BC stands for. You might see some people who use BCE. It's because they don't want to use Christ. They put before Common Era instead of before Christ. And then instead of saying Anno Domini, which made me start writing A instead of writing Anno Domini, they put CE for Common Era. Before Common Era and Common Era. What defines the Common Era? The birth of Christ. But it's a way for people who are atheists to not have to say Christ. Okay, so Pythagoras noted that when he was studying strings that were the same type of material and the same tension, why same type of material and same tension? Why is that important? What was the square root of tension divided by mass per length? That was the speed. So with strings that had the same wave speed, he found that it sounded really good when he plucked two strings if the ratio of lengths was a small integer ratio. So if the ratio was 4/3, 4 is a small integer, 3 is a small integer, 3/2, or maybe 1/2. When he had those ratios of the lengths, then they sounded good together. Now, using what we've learned, the frequency, the fundamental frequency, is equal to V over 2L. So frequency 1 over frequency 2, that is length equals 1, length equals 2, would be V over 2 times 1 over V divided by 2 times 2, which is just equal to 2. So you had doubling the frequency sounded good together. Or, as you can see, it's just inverting the 1/2. If you have the ratio of frequencies that sounds good together, and so on. So this is actually the basis for modern European music. I know Pythagoras was from over there in Greece area, but information tended to move back and forth in Europe, and that's where we have our Western ideas of what's music. And so it's this research that led us to that, hence why we're starting with this. If you take a class in world music, you might learn about different ways of making music and different notes they put together because they base it on different ideas. So, in music, we have a piano keyboard here. We have our notes going A, B, C, D, E, F, G. And the piano keyboard is showing just the white notes. Starting at C, this is a C scale. You play with a total of 8 notes in what we call an octave. Octave means 8 notes, right? And so the octave, 1, 2, 3, 4. Now what you notice in the octave is you're counting both the top and the bottom note. So there's only 7 distinct, and then you repeat. And the way these are defined is to try to hit those ratios that Pythagoras said sound good together. So we define things like an octave, 8 notes here. An octave has a ratio of frequencies of 2. So you double the frequency when you go up an octave. So if you go from middle C to an octave above middle C, you've doubled the frequency. But then we have other sounds that are good together, specifically the 5th, the 4th, and the 3rd. So what are the 5th, the 4th, and the 3rd? A 5th has a total of 5 notes included. It's not the number between. See, there's only 3 between. It's counting the starting and ending. But that's a 5th. And the 5th is TH F2 over F1 is equal to 3 over 2. You go to the next note, to the F, that is a C to an F, and you have a 4th, because you have 4 notes included, and that's F2 over F1 is equal to 4/3. And then a 3rd would be going from C to E, 1 note in between, spanning a total of 3 notes. And what ratio are you going to have for that 3rd? Just increment each number. I went from 2 over 1 to 3 over 2 to 4 over 3. So for the 3rd, you have 4 plus 1 is 5, 3 plus 1 is 4. 5/4 ratio. So those are the ratios that sound good together. And so we devise our music so we have those ratios in the music we make. It's not as nice as we would like to think, though. How many people here play musical instruments? Okay, we got half the class roughly. With your musical instrument, you of course have to tune the instrument. you're tuning the instrument so every instrument is playing the same fundamental frequency when you say middle C, right? And then those instruments are designed so you can play these other notes. But you can't really make the instruments play, well, you can't make most musical instruments to play in any key and play these ratios. You can make a musical instrument that it plays in one key, but then you'd have to change it to make it play a different key. And so we often have songs where we change key in the middle of the song. So we don't use this just tuning. We use a different variant, which actually I changed the order. It was right here. Now I've made it come after. But we use what we call an equally tempered tuning, which puts in, instead of a total of 8 notes, counting this first and last in an octave, it puts a total of 12 notes in. It puts 12 notes in, only 8 of those that you play. Why does it do that? Because we have a mathematical formula that we use. We say, for the equal tempered, I'm going to make the frequency of the nth note is equal to the frequency of my fundamental times 2 raised to the n over 12. So the frequencies move up by these factors of 2 raised to n over 12. When I get to the 12th note, I've now doubled the frequency. And so that's how the equal tempered scale works. It's based on math, and it gives you close to the right frequency. So when you play in this key and then that key, your harmonies will sound close to the best, but not the best. Part of the reason I was telling Denver is we were going over stuff, obviously we got to talk about what we're going to talk, he's going to do. Part of the reason I think that I really love to hear like a barbershop quartet or, trios, a cappella singing is because the harmonies sound so good together. And it's because traditionally when you're singing a cappella, you let your ears guide you and you sing the just scale instead of the even tempered scale. And so the harmonies have exactly the right pitches to sound good together instead of close to the right pitches to sound good together. Now, the first of our clicker questions. So, summarizing. Oh, actually, it's not yet. Here's summarizing, and then the first question comes after this slide. These are the meanings of the terms third, fourth, fifth, and octave. And just keep in mind, the octave is doubling. It's 2 over 1. The next one of these is the fifth. You just added 1 to the number on top and the number on bottom, so 3 halves. The fourth, add 1 on top and bottom, 4 thirds. The third, add 1 on top and bottom, 5 fourths. So now our first clicker question. A C major scale begins with do, as in do, a do, a female do. And oh my goodness, where's the question? I have things out of order. That's what was supposed to be next. This is showing frequencies for a couple different scales. This one here is the one that we use most of the time. This one here is the Pythagorean or just scale. And so if you compare the frequencies, you see that they're usually within 2 hertz. Some of them are further off. The closer they are to exactly the same, the better things are going to sound. But you can see there's, take for instance, where was it? This one here, 372.5, 369.599. It's a difference of 2.5 hertz. In terms of it sounding good together, that's actually a pretty big difference. But overall, this is the best we can do. Now, please be my clicker question. Yeah, there we go. A C major frequency or scale begins with do as middle C, and we're just going to go to 264 hertz. What you use for middle C actually varies. Like the tuning forks we're going to use in the lab on Monday, they have 256 hertz is what they call middle C. So, it varies. So we have middle C is 264, and the question is, what is the frequency for 1 octave above that? for the next do. Okay, our answers were not the most exciting outcome. I think this is a good one for you to discuss with your friends around you, because obviously we did not have a clear majority here. Didn't have any majority. John, right? Okay.
But since it's higher, it has to be higher.
So I did C is 8.
Okay, I'm going to assume that means you're done because you've returned to your seat, Michaela. So let's answer again and see if we move toward correct after careful discussion with our colleagues. We indeed did. The correct answer was this. Okay, so I heard Andrew say something pretty obvious. What was that, Andrew?
It's going to be a higher frequency, so it has to be higher than 260.
Right. It's a higher frequency, so it has to be one of the two that was a higher pitch, or well, a higher frequency, because see, in my mind, the words translate back and forth. Had to be one of the two that was higher. Since all but one got it, anyone should be able to tell me, how did you settle on 528 hertz? Right, octaves are 2 times the one you started with. So you just double 264 and you get 528. Okay, next clicker question. Now we're going, instead of from do to do, we're just going up to sol. Going from here to here. Still 264 hertz. Got one, Andrew? You're still not in, Andrew. Okay. Okay. All 8 said 396 hertz. Now, there are 2 ways to solve this. One is the logical way, and one is the way to actually get the right number. What's the logical way? It's higher frequency, so it must be higher pitch. And since it's not an octave, there was only one other option that was higher frequency and not an octave. Okay, the way to actually calculate the number was, if it is, well, we have to count, which interval was this? Okay, this was a fifth. And so fifths have a frequency ratio of 3 halves. And so I just take 264 times 3 halves. And that gives me 396 hertz. Remember, the units are vital. You've got to have the units there. Okay, a third question now. One that I believe, yeah, this one here you can't simply solve logically. A C major scale begins with Do, and now we're going to Fa. Do, do. All right, everybody went with the correct answer. That F was found, how big was this interval? A what?
Fourth.
It's a fourth, and for the fourth you have the ratio is 4/3. So we take 264 and multiply it by 4/3. And we get the 352 hertz. Now, I put the 440 on here. 440 is a concert A. Just want to have the concert A there in my sequence. Okay, now it is once again time for Denford to come up. We're going to look at beats. Beats is a phenomenon that occurs. Beats is a phenomenon that occurs when you have two frequencies that are close to each other. And if the frequencies are close to each other, I know this equation is way too small. The beat frequency, the frequency you hear for the sound getting louder and softer, is equal to the absolute value of the difference between the two. So Denford is going to play one, and we'll look at its frequency and whatnot, then play the other, and we'll look at it, and then we'll play them both and look at it. So, go ahead, do your thing. Apparently, I didn't hit monitor, I thought I did. Okay, now when you look at that, when I'm not talking, it's a very nice, smooth sine wave. Do the other one. Another nice, smooth sine wave. They sound like the same thing. Now I'm going to have them hit them both at the same time. You hear it getting louder and softer? And you clearly can see it. That's because we're having constructive interference, nearly perfect constructive interference for a while, then shifting to destructive and back and forth, because they're almost the same frequency. And if you change your position in the classroom, you'll hear it louder and softer at different times because you're different distances away. Okay, we are out of time. Thank you for your help, Denford. See you all on Monday. Yeah.